Good afternoon, physics people. Mr. Martineau here, bringing you today's lab, live lab, rather than looking at a simulation. And the goal of today's lab is to reinforce the topics that we covered using free body diagrams and application of frictional forces, right? So this is where we are today. This lab is designed to go along with the lecture that we already had on these. So any notes or free body diagrams or kinematic equations were probably already covered in lab. And of course, if you have any questions, you can ask me. So the first thing that we have to do is we have to determine the coefficient of kinetic friction for wood on wood. And so I have here a wooden plank and a wooden block, okay? And what we're going to do, and again, we covered what's happening here in terms of free body diagrams in the lecture previous to this, but we're going to now demonstrate this. So here's the deal. I have a spring scale right here. The spring scale will measure 0 to 5 newtons. Here is my block. Okay. So what I'm going to do is I'm going to pull this block at constant speed. And I'll show you how I know it's constant speed once we get there. I will then come over to this data table, and the weight, the pull force is the thing that I'm going to measure with the spring scale. The weight of the block has already been predetermined. So I already know what weight I'm going to be pulling, right? So this is the block with nothing on it. And then what I'm going to do is make the block successively more and more heavy. And then I will record the pull force necessary to make this block go at constant speed. So that's the goal right now.
Ms. Palumbo, could you contact the main office, please? Ms. Palumbo?
Sorry for that, I'm in a public high school. So every time we get some data, I will then put it up here. Your job is to put this data table into either Google Sheets or Microsoft Excel, and eventually you will have to make a graph of this data. And if you're not sure what graph to make, please consult the Word document that I have posted on this. It'll tell you exactly what you're supposed to graph. Okay, so here we go. So I'm going to take this spring scale, I'm going to hook it on the block. The block by itself weighs 1.3 newtons. I measured that before. I'm going to start pulling this block. I will know that it's going at constant speed because this peg will not kind of jiggle back and forth. It'll stay on the same number. So I'm going to do this again. So look what happens when I accelerate it. See how it came off, but the needle really, really violently went. Watch, I'll do it again. So constant speed. So that's when I was accelerating it, kind of jiggled back and forth. I don't want to do that. I want it to have the same number the whole time. And it looks like for this first one, I'm at about 0.2 newtons. So that first data point is going to be 0.2 newtons. 0.20 newtons. Now what we're going to do is we're going to do that again. I'm not going to so worry about making sure the needle is going constant speed this time. Okay, I'm just going to add some weight to it. That force right there represents, or this number represents, the new weight of the block with the mass on top of it. So no more calculations need to be done. I've already told you what the number is. So here we go. I'm going to pull it at constant speed. Looks like about 0.8 newtons. 0.80 newtons. Next one, put another mass on this. Here we go again. Neighborhood of, let me do that one more time.
That's hard to do.
Yep, 1.1. I'm going to say about 1.1. Obviously some experimental error on this. I'm okay with that. You know, it's look what I have to work with, right? One more block. .5 newtons, I think that's safe to say. I'm going to put another weight on it. Let's say 1.9. I think it's safe to say 1.9 on that. And last one. 2.3. All right, so This data, so this is the first trial, second trial, third, fourth, fifth, and sixth. This is the weight of the block increasingly getting larger, so as I was putting more masses on it, this is the pull force that I was pulling on the block with so that the block would move at constant speed. And if you were paying attention or looked at the notes on the free body diagram with this, you know the relationship between the weight, the pull force, the normal force, and the frictional force. I'm not going to go into that right now. Using this data, you will then make a not a Google sheet, you will then make an Excel graph. The point of making that Excel graph is to determine the coefficient of friction for wood on wood. We need that coefficient of friction in order to calculate our theoretical acceleration for M1 and M2 in a half Atwood machine for wood on wood. If anybody that just didn't know what I was talking about, that's just a string of words. But if you were paying attention while we were doing the derivation for this, you know exactly what I'm talking about. So now what I'm going to do is I'm coming over to here. So this is our half Atwood machine. I have used the same block. I checked it. This is the same weight block as the other block I used over there. It's the same size, not that that matters. I have the same plank as the other plank, so they're identical in every way. But now I have it set up as a half Atwood machine. So you should recognize the half Atwood machine. We have a mass here pulling down, and then we have a string, and that's going to pull this weight over here. Okay? So what we're going to do here is I am going to there's going to be a mass M1 over here. So the hanging mass is M1. The mass that's being dragged is M2. And we should know from our free body diagram that we have a expression for the acceleration of this system in terms of M1, M2, mu, and g, right? So we should have that all ready to go. So what I should be able to do is input any values of M1 and M2 and then calculate a theoretical A without ever measuring anything. But our point here is that we actually want to measure the acceleration of the system and then compare it to the theoretical value that I got just by using the free body diagrams. So like before, I'm going to do some trials here. I'd like to draw your attention to this data table. So the only things that we're going to, can you get all of it?
Yeah.
You all set?
I'll come closer for the headings.
Okay, so we'll have M1 is the hanging mass, M2 is the sliding mass, A theoretical is what you'll calculate and put here. We're not going to do that now. T is the time it takes M1 to fall, and then A is something that you're going to calculate later. And we do need one other piece of information that I'm going to put up on the board, and that is, I'm going to put it over here on the side. The distance, check that. The displacement of M1 is going to be the same for every trial. So we're going to call that delta Y, and that's going to be equal to negative 0.68 meters. So that's going to be important for the kinematics. We need that number, and I measured that beforehand. So M1 is always going to displace negative 0.68 meters. That is to say, M1 is always going to fall 0.68 meters every single time. Okay, so I have that preset. The other thing we need to know about this data table is that M1 is always going to be the same for every trial. We're going to do, where's my little post-it? Stay there.
Mm-hmm.
Oh, I put it over here. We are going to do 1, 2, 3, 4 trials. Okay? For every trial, the hanging mass will always be the same. It's going to be 100 grams, or 0.100 kilograms. So we're going to do 4 trials. Okay? M2 is going to change for every trial. So this first trial, M2 is going to be equal to 0.133 kilograms. The next trial, it'll be equal to 0.333 kilograms. Next one is 0.533 kilograms. And I bet you figured out the last one is 0.733 kilograms. I will be honest, I'm not sure if this last trial will work because it might be accelerating too much for me to actually measure it successfully. So we might be limited to this 3. So this is a question mark, this last one. We'll find out. Okay? So now all we're going to do is we're going to set this up, and now I'm going to time how long it takes M1 to fall for each of these different masses. Okay, that's the general idea. Okay? So, I should probably keep my marker uncorked. And so here we go. We're going to come to here. I have it set up so that my M1 is ready to fall. The first trial is going to be just the block. The mass of the block is 0.133 kilograms. I am set at 68 centimeters. Okay, let me turn on my stopwatch. The on button would help. Okay, here we go. In 3, 2, 1, go.
That's fast.
Yeah, so that's accelerating, obviously. So that's going to be 0.55 seconds. So I will write it up here. You can stay there if you want. We'll get it later.
Yeah, I'll come and
That
get a
was
picture.
0.55 seconds. So don't worry, we will show you the data after. Next trial. Let's reset. Back to here. I'm now going to make M2 heavier by 200 grams. So that's 0.333 kilograms. Let me reset. In 3, 2, 1, go. Look out for flying masses. 1.05 seconds. Second trial, 1.05 seconds. Oops. Yeah. Third trial. So we're gonna go. I should have, never mind. I'll shut up. All right, reset in 3. Wait. Okay. In 3, 2, 1, go. 1.67 seconds. Last trial. $200 more grams. Reset. In 3, 2, 1, go. Yeah, I think I'm gonna take that one. Calling an audible. So I don't want to take that last one because it stopped, which says to me that the system is going at constant speed, which we don't want. And the system has to be accelerating in order to prove our point. So what I'm going to do is I'm calling an audible. The last, and I'll change this on the data table once we get over there. The last mass for M2 will be 0.633 kilograms. Let's see if we get some better data on that. Again, we want it to accelerate. We're trying to prove acceleration. So if it goes constant speed, it kind of kills the point. So here we go. In 3, 2, 1. That
There
still
you
is
go.
pretty constant, but
Yeah.
I'm going to keep it just for now. We'll see how the data plays out. 2.12 seconds. So this is 2.12 seconds. Let me change this. This is 633 kilograms. So let's get all that data.
So there's the changed mass.
Yep.
There's your T.
Cool. So now your job is to take our derived expression for the acceleration of a frictional half Atwood machine and calculate A using these masses and the coefficient of friction that you got from this graph. Because that expression is in terms of M1, M2, mu, and G. Then you're going to figure out what the acceleration of the system is using the time it took to displace through that displacement, given that V naught is 0. So you look at your kinematic functions and decide which one of these functions can I use to figure out what A is, given that I know what delta Y is, I know what T is, and I know V naught is equal to 0. So that should pretty much narrows it down to one option. And you will calculate that and put that here. And then these two should be around the same number. There's going to be some error, but you have to decide if that error is valid. This one I have doubts about, right? We might find that when you calculate the acceleration, it, I don't know, maybe this says it's 0, right? And this says not. I don't know. We'll have to see on this last one. I don't know that it was accelerating, but I can't tell because I don't have any other measurement tools for it. So that's all the information. You have the video, so you can watch it over and again. Make sure this gets populated in an Excel spreadsheet, and so that it's professional looking. Make sure this gets in an Excel spreadsheet so that you can make a graph of this data, because the slope of this line will be the coefficient of friction. Everything else we covered in lecture. You have seen my abode, my other humble abode. This is my rather rundown classroom for my building that's how many years old? 70?
60.
60 years old or so? So
Yeah.
Yeah, that's us. This
Yep.
is the other home. So anyway, thanks everybody, and I'll see you at next class. So thanks a lot for watching. See you next time.